We're going to look now at the reactions, the electrophilic addition reactions of nitration, sulfonation, and Friedel-Crafts. Nitration adds a nitro group. Sulfonation adds a sulfonic acid group. And the Friedel-Crafts reaction can either add an alkyl group, and we call it Friedel-Crafts Alkylation, or an acyl group that has a carbonyl in it. And we call that Friedel-Crafts Acylation. For nitration, we mix nitric acid with concentrated sulfuric acid, and it adds a nitro group, NO2, to benzene, makes nitrobenzene. What happens is the sulfuric acid protonates the nitric acid, and the protonated nitric acid eliminates water, making an excellent nitrogen dioxide electrophile, a carbocation electrophile. So here's the mechanism. There's the sulfuric acid, a very strong acid. It protonates the oxygen in the nitric acid. And what happens is that the oxygen that it protonates is one that already has a hydrogen on it, and that actually is eliminated as water. When it eliminates as water, it makes this nitrogen dioxide cation, which is an excellent nucleophile. The positive charge resides on the nitrogen, or a lot of the positive charge does. And so what happens is it adds this electrophile. The pi system reaches out and grabs the nitrogen. This then makes a nitro group on there, but of course the aromaticity is lost, but the positive charge is stabilized by conjugation with the double bonds. And then a proton is lost to restore conjugation, and we end up getting nitrobenzene. To form a sulfonic acid, what we do is we take fuming sulfuric acid. This is a mixture of sulfur trioxide and sulfuric acid, concentrated. So the sulfuric acid protonates the sulfur trioxide, and of course is protonating one of the oxygens. This makes that into an excellent nucleophile, and the sulfur has a lot of positive charge on it, which is then grabbed by the pi system. Once it adds to the ring, then the positive charge that develops is stabilized by the double bonds, and a proton eliminates to restore aromaticity. So here's the mechanism. Here's sulfuric acid and sulfur trioxide. One of the oxygen is protonated to give you this carbocation. The sulfur then is attracted to the electrons that are in the pi system. They reach out and grab it. Remember, sulfur can have multiple bonds, but when the electrons reach out to grab it here, one of these bonds jumps onto an oxygen, and you can look at the Lewis dot structure that way. The addition of the sulfonic acid, or the sulfur protonated sulfur trioxide, gives a carbocation that is stabilized by the double bonds, and then the proton leaves to restore aromaticity, and we get something called benzene sulfonic acid. The sulfonic acids are useful because they can be converted to phenols, but you have to be careful. 300 degrees Celsius and sodium hydroxide is required, and 300 degrees Celsius and caustic conditions are very aggressive, and you can't have many groups on that benzene ring and this go ahead without numerous side reactions. In the Friedel-Crafts reaction, we make a carbocation that adds to the ring. So when the carbocation is on an all-carbon chain, then we have alkylation. So you choose an alkyl chloride that puts the whatever carbon chain you want on the ring, and you mix it with this catalyst, aluminum chloride. What happens is the catalyst reaches out and grabs the chloride and pulls it off the substrate, forming a carbocation. This is then an excellent electrophile. The electrons in the pi ring reach out and grab the electrophile. The positive charge is stabilized by the two other double bonds, and then the proton leaves to give you an aromatic ring. In order for this to work, the carbon that is in this alkyl group here must be sp3 because you have to form a carbocation. In fact, it's best if it's tertiary because primary carbocations we're going to see have a problem with rearrangement. You can also use chlorines and, fluorines and bromines and iodines in there. You use whatever is available to you and what's cheapest. If the aromatic ring is substituted with an electron withdrawing group, and how do you recognize an electron withdrawing group? It's going to be any substituent which adjacent to the ring has an atom double bonded to either nitrogen or oxygen. It's going to be very electron withdrawing, and this will prevent any Friedel-Crafts alkylation from occurring. Additionally, if it has an amine, the amine will be alkylated by those alkyl chlorides, and that forms an amine salt, which has a positive charge on the nitrogen, and that positive charge on the nitrogen eliminates the electrophilic character of the pi system in the ring. So either an electron withdrawing group or an amine on the ring causes no alkylation to occur under the conditions for Friedel-Crafts alkylation. So this goes through why it prevents it. Again, because the carbocation is a weak electrophile and it will not react with deactivated rings. We're going to learn what deactivates and what doesn't. And anything that either has a positive charge or has an electron withdrawing group on it, like nitro or sulfate, or even any compound that has a carbonyl adjacent to the ring, you will find that Friedel-Crafts alkylation or acylation, we'll see also, will not occur. And if there's amines, what first occurs is the amine reacting with the alkyl halide to form a salt like this, and that has a positive charge which ruins the electrophilic characteristic of the pi system. One of the problems with the Friedel-Crafts alkylation is that a carbocation forms, and so if you do happen to use an alkyl halide that is primary other than a methyl halide, what will happen is you tend to get rearrangement. Methyl and ethyl can't rearrange, and so to anything more stable, so they don't. But any other carbocation will rearrange, and what you will have is a mixture of products. So if you're looking at a reaction and the alkyl halide seems to have rearranged its backbone on addition, what happened is it did. And you can either have alkyl halide or hydride shifts occur, just whatever gives the most stable carbocation. Another problem with Friedel-Crafts alkylations is that once you add one alkyl group, that it makes the ring more want to add more faster. And we're going to look at this later, but this is a problem with the Friedel-Crafts alkylations. So there's two problems with the Friedel-Crafts alkylations. One is that you get more than one substitution, and then two, you often can have rearrangements of the carbocation before addition. The mechanism is as shown here. Here we have a secondary chloride, and that secondary chloride is mixed with a catalyst, aluminum chloride, which pulls the chloride off the alkyl halide. Once it does that, the carbocation is attracted to the electrons in the pi system and does an electrophilic addition. Once it adds to the pi system, a proton leaves to restore aromaticity. This is a Friedel-Crafts-like alkylation. You don't use aluminum chloride and an alkyl halide. What you do instead is you protonate an alkene to form a stable tertiary carbocation, and that tertiary carbocation then will add to the ring. But this has the same problems as with the Friedel-Crafts alkylation, is that you can get multiple additions. What you can do in addition to the alkylation is what's called an acylation. And with an acylation, what you're doing is you're adding a carbon chain that has a carbonyl adjacent to the benzene ring. So it looks like an alkylation, except that the carbon adjacent to the benzene ring has the carbonyl. The reagent that you use is an acid chloride and aluminum chloride again. The aluminum chloride will remove the chloride from the acid chloride, and the acyl cation is formed. This cation is actually stabilized by the adjacent oxygen. You would think that the electron withdrawing oxygen is destabilizing to a carbocation, but actually stabilizes it because it has non-bonding pairs that it can donate, lean over to the carbon that has a positive charge on it to stabilize that positive charge. This is an excellent electrophile and ends up adding to the ring. Here's the mechanism. This is propanoyl chloride. The aluminum chloride removes the chloride actually, and it forms this carbocation, the acyl cation. This adds to the ring, and then a proton leaves in order to restore the aromaticity. The benefit of acylation is, one, there is no rearrangement of the cation, and two, once this adds, it only adds one time because the carbonyl actually makes the ring less likely to be substituted because it's electron withdrawing. And we'll again look at this later in some later online lectures. So acylation and alkylation occur by the same mechanism, including the same catalyst. It's just alkylation is limited in its usefulness. Acylation is not limited. The wonderful thing about acylation is that you can reduce that carbonyl down to a methylene group so that it is just like alkylation. So what conditions will add a nitro group to benzene? What you need is nitric acid and sulfuric acid. Remember that the sulfuric acid adds a proton to this and then it removes water, giving you NO2, which is basically a nitro group. Of course, it's a nitrogen dioxide cation that adds to the benzene ring. What conditions will change benzene to acetophenone, shown here? Well, to do this, you need to do a Friedel-Crafts acylation. The conditions for Friedel-Crafts acylation is to use the acid chloride and aluminum chloride. What are the limitations of Friedel-Crafts alkylations? Well, first of all, multiple alkylations are a problem. Next, carbocations formed can rearrange. The third problem is that electron withdrawing groups and amines will prevent Friedel-Crafts alkylation from occurring. These also will prevent Freidel-Crafts Acylation from occurring. So when you have electron withdrawing substituents, that Friedel-Crafts alkylations or acylations will not occur. So what are the conditions to change benzene to benzene sulfonic acid? Well, to change benzene to benzene sulfonic acid, you need to do a sulfonation. Sulfonation conditions are sulfur trioxide and sulfuric acid. The sulfuric acid protonates the sulfur trioxide, which then is the electrophile that adds to benzene. Give two methods for making T-butylbenzene. Well, one method would be to do a Friedel-Crafts alkylation. So you use T-butyl chloride and aluminum chloride. Another method is to use 2-methylpropene and sulfuric acid, which would protonate the 2-methylpropene and allow it to add, make a carbocation, which would add to the benzene ring. Of course, both of these methods are limited by multiple alkylations, and if you did this, you would have to separate your single alkylation product from your dialkylation product.